on Muto Online. My name is Teacher Mugulumiza Noah, a physics facilitator for today. Today, I happen to bring to you something very new and interesting. From one of our previous videos, we had already introduced pressure, and in this video, we are basically going to look at the transmission of pressure in fluids. After having looked at the exertion of pressure in solids and liquids, now we want to basically now look at how pressure is transmitted in fluids. So we have transmission of pressure in fluids. Now, a fluid is a substance which can power. Now, pressure is transmitted in fluids basing on what we call Pascal's principle. Hope you've already heard of this before from your research, or maybe you already looked at it. So I'm just here to actually make a point of emphasis and direct you on how and where to do what. Now, for liquids to transmit, it works on what we call Pascal's principle. Pascal's principle. A physicist in the names of Pascal came out with this idea, and Pascal's principle states that pressure applied at any enclosed part of a fluid, an enclosed part of a fluid is transmitted equally in the fluid and in all directions. We're just going to digest this and we'll simplify it much better. That pressure applied at an enclosed part of a fluid is transmitted equally in the fluid and in all directions. I want to bring this real life scenario. Get a bottle, a plastic bottle. Then this plastic bottle, you fill it with water. Then this top here, you tighten it and cover it. When you try to push this top here of the bottle, you apply a lot of force on the area. If this is my bottle, it has a top, a fluid in it. In this case, it is water. It can be any fluid or liquid, as long as it's not alcohol. Now, when I apply force, remember pressure is force over area. So when I apply force here, much force, when this fluid is filled, now pressure will be created inside the fluid or inside the water in the bottle here. And when pressure is exerted in here, it will be distributed equally inside the whole of it. Now what will happen is that because of the equal distribution of pressure inside this water bottle, this down part here at the bottom of it will end up blowing off. It will just go off. Why? Because of the too much pressure, which is equally transmitted throughout it. Now, let us just do a simple experiment to verify Pascal's principle, which states that pressure applied at any enclosed part of a fluid is transmitted equally in the fluid and in all directions. So we have an experiment to verify Pascal's principle. Verify Pascal's principle. Now we shall have the materials required, and in the materials required we shall have a piston. Then we can have a round bottomed flask. Some of these materials you can actually improvise if you don't find any within your means. Then we shall have water, and then we can have also coke. Then you can have a drill. Now, arrangement of our apparatus. Arrangement. So I'm just going to have a simple arrangement of our apparatus here. This is my round bottomed flask. Then I said I need a piston. This is my piston, like that. This piston that I'm going to use for pushing. Now I'll have different holes. I'll have this, can call it hole 1, can punch here hole number 2, hole number 3, and maybe hole number 4. Now, these are the procedures on how you're supposed to handle this after you arranging it like this. 1, you get your round bottomed flask. You're going to help me and punch or drill holes of equal sizes around the surface of this round bottomed flask. Now, after, you're going to first fix cork, this cork here, such that our water cannot run out unless we need it. Now, after fixing the cork in the holes that are punched on this round bottomed surface, you're going to fill this round bottomed flask with clean water, fill it with water. Then you bring your piston here. Now, we already know that pressure is force over area. Now, we are going to apply force on this piston around this area here. So I'm going to push this piston here and it squeezes the water. Now, when I apply force here, or when I push this piston here, pressure is going to be created. And when pressure is created, according to Pascal's principle, it is going to be transmitted all over the fluid or all over this liquid here equally. And when it is transmitted equally all over the fluid, these corks here, they are not permanent. And so they will each blow off. And it will be observed that in your observation, that water will come out in these holes that are punched on our round bottomed flask at the same pace. And the pressure will be the same. The speed at which the water from different holes will come out will be the same. Why? It is simply because it is the same pressure which was equally transmitted within the fluid. So basically that, in case you happen to maybe verify Pascal's principle, that is a simple experiment that you can use. You have a piston around the bottom of the flask, you can use any, then water and the cork. Punch holes around it, but those holes should be of equal sizes. Fix their cork. After fixing their cork, you now fill it with water. Why do we fix cork first? Such that we keep our water not moving out, not until we need it. Then after, you now push this piston inside and you exert pressure. So when you exert pressure, it will be created in here and it will be equally transmitted all over the water. And then water will come out from different holes at the same pace. Hence, Pascal's principle verified. Now, on that note, therefore, we have to look at applications of Pascal's principle. Applications of Pascal's principle. Pascal's principle is really very important. Application of Pascal's principle. In physics, we don't study what is not applied in our day-to-day life. Whatever we really study, we experience it in day-to-day life, either knowingly or unknowingly, depending on the level of physics literature that you have. Now, we have quite a number of applications or uses, but I'm just going to cite out a few. Before, have you ever asked yourself how a small car jack, when I talk of a car jack, there is a small car jack or hydraulic car jack. There is a small machine mostly used by the mechanics when they are repairing vehicles. They always pump it slowly, then it lifts a heavy load or it lifts a heavy car. Then when that car gets up, they can now make any maintenance beneath the vehicle. That hydraulic car jack, it is working, or it works on the principle of Pascal, or it works on Pascal's principle, which is the pressure. So inside that car jack, there are some fluids. So when they apply some force on one of the pistons, because it has two pistons, as we are going to see, a smaller piston and then a big piston. So when they apply some force on a smaller piston, Pascal's principle will now come into action. Pressure will be created and equal transmitted through the fluid. And so it will also cause the piston adjacent on the other side to raise the big load or raise the big car. And you do any repair or maintenance. So to cite out some, used in hydraulic press, used in hydraulic jacks, used in hydraulic brakes, among others. These are all applications of Pascal's principle. When you talk of hydraulic brakes, you've seen so many vehicles, mostly the cool runners that are commonly or locally called Lukulana, but they are called cool runners. Now, such vehicles or such heavy vehicles, their brakes work on Pascal's principle. When it is going to stop, when you apply some brakes, you always hear some gas piercing out because of the pressure. So whenever that person applies force on the foot pedal or on the brake pedal, then he or she is trying to apply some Pascal's principle of pressure to apply such that the vehicle can stop. Okay. Now in this, we are going to basically look at a hydraulic jack, hydraulic jack in particular. That a simple machine, pump-like, that most these mechanics use when they are repairing vehicles, mostly to lift and increase on the height of the vehicle, or maybe when the vehicle has got stuck or has slided, anything. Maybe it has got stuck in the mud, or maybe the tires burst, and they need to replace it with a new tire. They always use this machine. So we shall first of all have its structure. So it has a small piston. I can have this smaller piston here. Then we have a bigger cylinder this side. This is our piston. This is our piston here, right here. Then we have another piston on this side on a bigger cylinder. So this piston is a little bit bigger than the first one, like that. Now, This piston is where our load is going to be put. Now, we are going to apply, here we shall have pressure P1, and here we shall have pressure P2. Then we are going to apply force F1 here. This force F1 is being pushed to this area here from here to here is very small. So I'm going to also call it area 1. Then this side we shall have F2 and we shall have area 2. The structure of our hydraulic jack, that is if you are required to actually briefly describe the structure of this hydraulic jack. It is simple. When you look at this hydraulic jack, it consists of a small piston. This is a piston that is fitted in a smaller cylinder on one side. This is a cylinder. This is a cylinder. Smaller piston fitted in a small cylinder. And it has a big piston still fitted in a big cylinder. So this is a cylinder. It is relatively bigger than the first one. Then even the piston is also relatively bigger than the other. Now, inside here, we are going to have a fluid. A fluid. Why do we honestly use a fluid and not a gas? Hey, that is also an important issue to note. Now, we shall take, or Pascal's principle takes into an assumption that fluids that we are going to use here, fluids must be incompressible. Incompressible. From the simple literature of it, incompressible, it cannot be compressed. It cannot be squeezed, unlike air. So, we use fluids because fluids are incompressible, such that when I try to compress this fluid at one point or using piston 1, it refuses, and so it just exerts pressure, and this pressure will be equally transmitted all over this fluid. Now, fluids are used in hydraulic press simply because fluids are incompressible, they cannot be squeezed. And Pascal's principle assumes that the fluid used is incompressible or must be incompressible. So, now this is how it works. You apply a force. We are assuming the cow that we want to lift up is put down here. Then I keep applying up and down this piston. When I place this piston here, it is going to exert pressure in this fluid here. According now to Pascal's principle, that pressure exerted at one end of an enclosed fluid. This fluid is enclosed. It is within the tubing. Pressure is transmitted equally in all directions. That means if I consider Pascal's principle, pressure will be created here, and according to Pascal's principle, it is going to be equally transmitted all over the fluid. And since this liquid is incompressible or cannot be compressed, it is going to force this bigger piston to move up. As this moves down, this moves up. And when it moves up in the due course, the rod here that is put here, in our case in a point can be a vehicle, it's going to be lifted up and the mechanic can do his or her work. Physics is interesting. Let's look at some calculations. Now, before we look at some calculations, we have to note this formally. That for P1 to get pressure 1, it is force over area. So it is force over area. So P1 equals, but the force we used, we nicknamed it F1 over area 1. I put it there. Similarly, I need to get pressure number 2. So pressure 2 on the second piston is also force over area. So that force we don't know it, but we nicknamed it F2 over area number 2. Now, but from Pascal's principle, we say that pressure is equally transmitted. Now, from the simple knowledge here, it automatically means that P1 is equal to P2 according to Pascal's principle. When pressure is exerted at one end, it is equally transmitted throughout the fluid and in all directions. So that simply tells us that P1 is equal to P2. So we shall simply now say that P1 equals to, this means that pressure 1 is equal to pressure number 2. If this is then mathematically correct, then we just bring now the feelings for P1, which is F1 over A1 is equal to F2 over area 2. Now, this is okay. And supposing you have F1 area 1 and you have F2, but you don't have area 2. So it can be mathematically simple to come up with area number 2. Some people can even write it in this form, or you can say F1 over F2 is equal to A1 over A2. When you cross multiply and you rearrange, still it is the same formula. When this comes here and that goes there, it is still the same formula. So in books, different resources, if you find this or you find this, it is the same. Now here, let us look at a simple example. We are going to consider a figure with a hydraulic press with piston is A and piston is B. So this is a hydraulic press like that. Now this hydraulic press, it has two pistons. It has piston B here, and it has a smaller piston in the names of A. Then it has the fluids inside it, which are incompressible. They cannot be squeezed. Now, on side A, there is a force here, which is 600 Newton is applied on piston A, and the area A1, the area here, we can have 2 meters squared. Then side B, we have area of 5 meters squared. Then F2 equals to unknown. Now, in our question, they want us to find the force exerted on the piston B if a force of 600 Newton is applied on piston A. So, they want us to come up with F2, or the force on piston B, if we apply a force of 600 Newtons on piston A, which has a cross-section area of 2 meters squared, and then that of B, it has 5 meters squared. So we shall just simply use this relationship that you say, recall that F1 over A1 is equal to F2 over A2. Now, this is just given as F equals 600 Newtons. What you need to do is just baptize it. You call it F1 and then call this area 1. The reverse is true on the other side, F2 area 2. But remember, area should be in the standard unit. It should be in meters squared. Now, we just now to put back or substitute in our formula here. So F1 is given as 600 Newtons. Area 1 is 2 meters squared. Should give us F2, which is unknown, and it's what we are looking for, over 5. Now let us cross multiply. When we cross multiply, or when we reduce before, we can have now 600 times 5, giving us 2f. Now 600 times 5 is equal to 2f over 2 over 2. Now, since this is multiplication and it is not addition, it is mathematically advisable, it's mathematically very right to cancel this and that. But in case here it is not multiplication and it is addition, never tamper and say by 2 by 2. But if it's multiplication, it is very, very perfect and fine. So when we reduce this by that, I don't love to cross out. When you cross out, it means that whatever you're doing is wrong. That's why you've crossed out. So don't cross your work. It will look untidy. Use a calculator scientifically. So we have now 300 times 5 giving us f. Now, we make f the subject, 5 times 3, that is 15. Then you bring these ones, and then f is measured in newtons. So you see that F2 here, F2 is 1,500 newtons. So when you compare first one, we had 600 newtons, then F2 is bigger than F1 equally because area 1 is also smaller than area 2. So basically, this is application of Pascal's principle. You always see people pressing on the brake pedals whenever they want to stop. Such vehicles, like the cool runners, as told you earlier before, they work basically on Pascal's principle. For now, I welcome any questions in case you have any. I'm around, ask any questions, and you get answered right away. In the meantime, Jemima, you're welcome. I can see you here. Then we have Hadax Genis, you're also welcome. Ruth Navada, thank you. You're welcome. We have Mugisha Kevin, you're also welcome. Share the live to other people and also encourage them to subscribe to Muto Online for more reading materials and the simplified new curriculum work. Otherwise, I'm not seeing any question here. I'm seeing Ruth Nabada saying I got 1,500. Perfect. That is the answer I've also got. Nabada, let's get that. I think there's no question here. Thanks for listening. Tune in the next videos. Thank you.